overall reflection of an object. That's total internal reflection. Okay. And there are conditions necessary for this total internal reflection to occur. Okay. First of all, the light must travel from a denser medium to a less dense medium. So, number one, the conditions necessary is that the light must travel from a denser medium. Denser to where? Less dense. That's denser medium, for example, air. To what? No, denser medium is water to air. So this one is example, e.g. water to air. Then the second condition for total internal reflection is the angle of incidence must be greater than the critical angle. Number two, angle of incidence must be greater than what? Critical angle. Angle of incidence must be what? Greater than critical angle. So what are the applications of total internal reflection? Is applied in mirage, prism, and optical instruments. Okay, applications. Okay, in mirage, optical instruments, and prism. And what? Prisms. All right. Hope we know the meaning of mirage. When when air goes close to the ground, when air is trapped close to the ground. So when you look at it from afar, you are going to see it as water on the road, especially when you are on the tide road. So when you look at it from afar, you see the mirage. The mirage appears to be as if the road is wet with water. But when you get there, there's no water there. It's just air that is cooled and air hangs above the surface of the tide road or the ground or the floor, whatever. Whatever place that the mirage is formed. So because of that total internal reflection, the total reflection in the system, that's why you get mirage. It's also used in optical instruments like in periscope, kaleidoscope, in prisms too, reflection. I also gave you an example of fish in water. Because of the total internal reflection between the body of the fish, the lighter body of the fish, the lighter part. You know that usually most fish, the underside of their body is usually reflective. It's usually non-luminous. Okay, so the total internal reflection from the body of the fish and the water affects the transmission of wave. Okay, transmission of light ray from the water, which is what? The denser medium, to air, which is less dense medium. That's why when you are above the water and you are trying to look at the fish in the water, you are going to see something different because of total internal reflection. So this is one of the conditions necessary for it to what? Occur. Okay, it must be from a denser medium to a less dense medium. All right, so the light is traveling from the water to you, that is outside the less dense medium. All right, the second condition is this one. Okay, the incident angle, the angle at which the light ray is incidented into the medium must be what? Higher than the what? The critical angle. That's that for total internal reflection. So like I said before, I already told you the applications. It's also applied in optic fiber. Dispersion of light. That's what we are looking at next. Dispersion of light. Dispersion of light. I think this is going to be the last class. Okay? Last class in physics. So dispersion of light is something that occurs because we need dispersion of light to separate various components of light. You know, when you separate white light from its various components, or you split white light into its various components, because white light is like the father of other light. It has several other components. So the dispersion of light is separating light into its various components. That's dispersion of light. As simple as that. All right, dispersion of light. All right. So light is dispersed or separated into various colors known as electromagnetic spectrums. All right. And dispersion is usually done with a prism, with the help of a what? A prism. That's what we usually use for the dispersion of light. Okay. So in the dispersion of light, which of the light bends most and which bends least? We are going to find that out. All right. And for pure spectrum dispersion, you know, we use this one, this prism for white light. Okay. For white light dispersion. Okay. For white light. Then if you want to disperse a pure spectrum, we use a slit. All right. Use a slit for pure spectrum. All right. That's for monochromic light, light of one wavelength. Monochromic light. Is it monochromic or monochromatic? Monochromatic. Monochromatic light. Okay, light with one wavelength. All right. So before that, we are going to look at the acronym when white light is separated to its components. There is an acronym for it. It's called the Rooigraph. That is known as rainbow. Okay, rainbow has 7 colors, right? So it's the Rooigraph. Okay, R stands for red, O stands for orange, Y stands for yellow, G stands for green, B stands for blue, I stands for indigo, V stands for violet. So these are the components of white light, all right? The colors of white light. So this one, the last one, which is violet, is the what? The most scattered or the most separated. This one is the most what? The least separated. That's the first one, red. So this is usually the first to separate. This is usually the last to separate. All right. Don't forget that. So when you are going like this, is what? Increasing separation or increasing dispersion. When you are coming like this, is decreasing dispersion. Okay. These are parts that questions are commonly set from. Let's understand primary colors and secondary colors. Also, addition of colors. So this rainbow you see here, it occurs as a result of what? Dispersion of light. Dispersion and reflection. So dispersion plus reflection gives us rainbow. Okay, that's a very common question. Let's look at primary, secondary colors. Primary colors are the what? ROGB, right? Primary colors are what? ROGB. Primary. We have ROGB. RO is red, G is green, B is blue. Secondary color is the color gotten from addition of what? 2 primary colors. Abinobi so. You add red and green. Red plus green will give us magenta. Red plus green equal to magenta. This one is secondary color. Red plus blue will give us cyan. Then red plus, we've done red plus green. So we do green plus blue. Abi, is green plus blue yet now? Okay, it's green plus blue that will give us cyan. Plus blue will give us cyan. This one will give us yellow. Cyan. Okay, so that's that for that. So these are secondary colors. All right. Then tertiary color. How do you get tertiary color? You add one here, one secondary color here. You add one secondary color to one primary colors. Okay, to get tertiary color. All right, but let's leave that one. There is this concept called object colors. Object colors. Okay. these object colors are colors that absorbs all colors, but reflects only one. So object color is capable of absorbing all colors, but reflecting only one color. And that is responsible for the appearance of an object, the color that you see, okay, when you look at an object. All right. So, and these object colors include, when you have red and you have rose in an object, okay, red is reflected, okay, red rose reflects only red. This is an object color. Absorb any other color and reflect just one. Reflect just one, which is what? Red, but it absorbs every other colors. All right. So we have color filters. Color filters helps to what? Transmit a particular color. It filters the rest. Maybe you just want only red. It filters the rest and transmits only red to you. Okay. What is the reason why objects have colors? It's because they reflect certain wavelengths of light and absorb others. That's where you have this object color now. Certain wavelength of light, and that's what that object can reflect. Then other colors are absorbed. All right. For example, a red object reflects red lights and absorb every other colors. Remember what we talked about? Objective colors. We've talked about monochromic light, single wavelength, or monochromatic light, a light with single wavelength or single color. Example is like laser beam. That is one of the most classical example of that light. Now let's look at electromagnetic spectrum. Okay, electromagnetic spectrum. This is where you have the Rayleigh wave. Is it Rayleigh wave? Revox G. All right. So in the electromagnetic spectrum, this is the separation of electromagnetic wave into its components. Writing out all the components of electromagnetic wave, we have Revox G. Okay, and here R stands for what? Radio wave. I stands for what? Infrared. V stands for visible light. Sometimes in some old textbooks, you can have microwave here. In some old textbooks, you can have microwave here. Okay, you can have then the next is U, ultraviolet light. You have S ray. You have the last one, gamma ray. All right. So here, as you go from left to right, here now, as you go from left to right in the Revox G, is what? Increasing frequency. All right. Then when you go from left to right, from left to right, is what? Decreasing, increasing, what do you call it? Wavelength. All right. From left to right, increasing wavelength. So in essence, here is increasing frequency when you are going towards this dimension. Increasing frequency and decreasing wavelength. So the highest wavelength will be this one. Radio wave. Then the smallest wavelength will be this one. Okay. So this one is, that's increasing frequency, decreasing wavelength. So when you are coming like this, okay, that's from left to right, you are now going to have what? Increasing wavelength, decreasing frequency. Okay, don't forget that. So it's just like here now. If we are going down, we are going to have what? From radio wave, this is what? Increasing frequency, decreasing wavelength. Okay, so when we are going up, we are going to have what? Increasing wavelength, decreasing frequency. So this one, gamma ray has the shortest wavelength, radio wave has the longest wavelength. Gamma ray has the shortest frequency, radio wave has the highest frequency. So that's that for that. So what is radio wave? Radio wave is the source of radio wave is through natural source or transmitters. It is detected with what? With a wireless communication network or radio. And it's detected with a radio detector. Radio wave detector. Therefore, microwave is the source of microwave is through a hot body. Okay, hot body. All right, and is detected with a thermopile, hot body. All right. The infrared wave is you get infrared wave from a very hot body, hotter than like 100 times hotter than microwave. All right, and is detected with a thermopile, thermopile. All right. We have visible light. Visible light, the light source is like the sun. You understand? Visible light is through a light source now. Is detected with what? Visible light is detected with the eye and ultraviolet sensors. No, that's ultraviolet ray. The eye is the eye, or you can use camera to detect visible light too. Any photosensitive, Therefore, the ultraviolet ray is the sun. Okay. The source is the sun, detected with what? The eye can also detect ultraviolet ray, UV detector, ultraviolet light detector too. Therefore, X-ray is through radiation or radioactivity. All right, both X-ray and gamma ray both are through radioactivity, and they are detected with what? Both of them detected with Geiger Muller counter. All right, take note of those. What are the uses of each of them? Radio wave is used to transmit signal. Okay. Microwave, the same thing, used to transmit signal. Infrared can be used to transmit signal. Okay, and can be used to heat up a substance. Visible light is used as what? Light source and what? Source of heat. Ultraviolet light is used as light source, also as what? Source of heat. Also used during photosynthesis by plants. Okay, absorption during photosynthesis by plants. X-ray is used for what? Treatment of cancer. It can also be used for tracing, okay, to create tracers. It can also be used to detect leakage in pipeline. X-ray and gamma ray, both of them. All right, they are also used for radio activities. All right. Let's look at electrostatics. Electrostatics. All right. Electrostatics is the induction of stationary charge. Charge that doesn't move. That's why you can see statics there. We have electro there. We have statics. Electro is charge. Statics is something that is not moving. Stationary. Stationary charge. That's electrostatics. All right. So stationary charge. So a positive charge is known as proton. Negative charge is known as electron. Okay. Positive charge is known as what? Proton. Negative charge is known as what? Electron. All right. So how do we form positive charge and how do we form negative charge? Charging a body is called induction. Okay, there are different ways to charge a body. You can charge a body through induction and through what? There are two ways to charge a body. You can charge a body through contact and induction. Contact and induction. Contact is where you bring the body closer to a charged body. Induction is where you induce current in the body. You connect something, a charged substance. You connect a charged body. You connect it directly to that body to induce current, or the body itself forms the charge and start up the charging process. That's what induced charge. All right. So making positive charge, we usually use what? You induce positive charge with cotton on silk. When you rub cotton on silk material, you get positive charge. Then for negative charge, when you rub 4 on ebonite rod, you get what? Negative charge. All right. Charge is detected with an electroscope. One of the most common electroscope is the gold leaf electroscope. So that's one of the most common electroscope. Electric field E is equal to charge over force is the force per charge. Okay. Electric field is the force exerted per charge, where F equal to force, Q equal to charge. Electric field intensity electric field intensity, electric field intensity is equal to the force per charge, force per unit charge, force per unit charge at a point. This at a point is very important too. At that point, at the point, the force per unit charge at that point. All right, that is electric field intensity. Okay, there is also electric potential V, electric potential, which is our V, equal to K Q over R, where R is area, Q is charge, K is for what? The constant. So in essence, we are left with Q over R. Okay, charge per cross-section area, electric potential. What is the potential difference? The work done in moving units positive charge from one point to another. So the work done that moves potential difference, is the work done of moving one unit positive charge from one point to another. That is what? Potential difference. Electric discharge or lightning, you know that one at thunder. Let's go into Coulomb's law. Coulomb's law of electrostatic force. Coulomb's law. Remember, it's Coulomb's law that states that like charge repel or like charge attract. So positive charge will be attracted towards a negative charge. All right. We already talked about this in chemistry. So when we have positive, they are going to what? Repel. Okay. They don't want each other because they are the same. It's just like same-sex marriage. Gay. Now gay they be. You know if you work. But plus, minus, we attract, marry. All right. This is what Coulomb's law. But let's now look at the law in full. Okay. The Coulomb's law in full. Coulomb's law. Coulomb's law states that the electrostatic force, which is F, equal to the electrostatic forces between 2 points, which is Q1. This one is the first point, Q2. 2-point charges. The electrostatic force between 2-point charges is directly proportional. That's why we have equal to here. It's directly proportional to what? To the product of the charges. That's why you have two of them together here. And inversely proportional to the square. We'll now put over to put the inverse proportionality to the square of their what? Distance apart. Okay? So the electrostatic force between 2-point charges Q1 and Q2 is directly proportional to their product and inversely proportional to what? The square root of their what? Distance apart. Then we put constant here. K stands for constant. Q1 stands for point charge 1. Q2 stands for point charge 2. All right. Over R squared, which is what? The square of their what? Distance apart. So this is Coulomb's law. All right. So we can therefore rewrite this as F is equal to Q1 Q2 over R squared. Okay. So when we remove this square, if we are not squaring the distance, we now use square root. Therefore, F is equal to the square root of Q1 Q2 over R. All right. So that's that for that. Okay. Square. How to square. So you are either using this or you are using this. All right. So therefore, there is something called permissivity of free space. All right. Permittivity of free space. Permittivity of free space. This permissivity of free space is the space required for electricity to be transmitted in a vacuum. All right. It's usually given as 1 over 4 pi E naught. 1 over 4 pi E naught. So we can as well bring this to Coulomb's law times Q1 Q2 over R squared. All right. We put our force here times force equal to this. Okay. But when we are solving, we are going to use this permissivity of free space as constant. We say therefore F is equal to 1 over 4 pi E naught Q1 Q2 over R squared. All right. So we can use this to solve depending on the nature of the question. This permittivity of free space is given as a constant, you know, the value of this E naught here. This E naught here is the permittivity of free space given as E naught. All right. So the value of this E naught, it has a constant equal to 8.85 times 10 raised to power, is it not, minus 12 Newton, okay, Coulomb first, Coulomb square per Newton meter square. So this one is permittivity of free space. That's like the contact, the constant. All right. Then there's something called constant of proportionality, which is this constant that we spoke about here. This one. When you now bring permittivity of free space, everything together, it's called constant of proportionality. Of proportionality. All right? It's given as 1 over 4 pi E naught. Everything. Permittivity of free space and 1 over 4 pi. That's where you get constant of proportionality. And it's equal to 9 times 10 raised to power 9 Newton meter square per coulomb square. All right? Now the same thing. You can see. So, if you are using the whole of this to solve, you are going to use the constant of proportionality. But if you are giving permittivity of free space to solve, you are going to use only permittivity of free space to solve. But everything is called constant of proportionality. So it all depends on the nature of the question. So if in the question you were given constant of proportionality, you use constant of proportionality. But if you were given only permittivity of free space, you leave this constant of proportionality, you include your permittivity of free space where you have this E naught. So if we are to include that, we are going to have, let's go to capacitor straight up. After this, we are doing capacitor. We have 1 over 4. What is pi? Times 22 over 7. What is E naught? This one. 8.85 times 8.85 times 10 raised to power minus 12. So this is what you are going to have. Okay? So that's that for that. Let's do capacitor. Very sweet topic. Capacitor. Very interesting. Capacitor. Capacitor. When you look at your old textbook will tell you that a capacitor is a condenser that can store electric current. That's what your old textbook will tell you. Okay? So we say it's a device that can store electric charge. So what it means is that there's a constant word there. Storing or constant expression. Something is constant. Storing of electric charge. Okay? Storage. That's capacitor for you. So capacitance is the ability of a capacitor to what? To store charge. Remember, it's charge we are storing. Storage of charge. All right. There are different types of capacitors. We have parallel plates and we have electrolytic capacitor majorly. So for the parallel plates, capacitor is the parallel plates are connected parallelly. Something like this. Parallel. You have in capacitor you have to plus. Okay, let's say C1 plus C2. So these are parallel plate capacitors. It's connected like this. C1 plus C2. All right. Then when you have capacitor connected in series, this is parallel. In series, it's like this: 1 over C1 plus 1 over C2 and so on. Okay. Don't forget that it's different from what you have in resistance. Okay, it's different in resistor. It's opposite of resistor. All right. So the parallel plate capacitor is usually used to store electric charge. To store charge, then the electrolytic capacitor. The electrolytic capacitors has a higher capacitance. All right. They have what? Higher capacitance. Big C, capital letter C is capacitance, and they are used in circuit for filtering current. Filtering current for what? Filtering current, or smoothing current. All right, that's the function. So we have to understand the capacitance. What's the capacitance of a capacitor? The capacitance of a capacitor is the ability of a capacitor to store charge. That's the capacitance of a capacitor. So it's given as C is equal to Q, which is current, over V. All right, whereby V is volt, V equal to volt or EMF. All right, Q is equal to charge or coulomb. Charge or coulomb. All right. So it can also be given as capacitance equal to, we have EA. This A stands for the area over the distance. All right. Remember when we were talking about Coulomb's law, okay, this E stands for what? Permittivity. So this is permittivity area equal to permittivity area. D is equal to distance. As simple as ABCD. Nothing hard for there. Okay. Let's now look at the factors affecting capacitance of a capacitor. Like I said before, in capacitance, it's not like in resistance. So in capacitance, when you have capacitance connected in series, in parallel, just plus all the capacitors to get your answer. But when you have it connected in series, that's when you are going to do 1 over C1, 1 over C2, depending on the number of capacitors you were given. All right. So that's how you solve for that, following the normal law. The normal law of solving it. Okay, so if it's connected in series, for example, if it's connected in series, we are going to do 1 over C1 plus 1 over C2 plus 1 over C3 and so on and so forth plus 1 over C3. Let's say, for example, C1 is equal to 1 farad, C2 equal to 2 farad, C3 equal to 1 farad. This is how you are going to solve this thing now. The SI unit of capacitance is farad. Before I forget. So we have other smaller units like microfarad. We have the bigger units like megafarad. All right. So now we have smaller units too like ufarad. Okay. This capacitance of a capacitor. Okay. Either Q over V or A over D. All right. So say we want to solve this one now. Say we want to solve this one. What we have here now, this one. 1 over C equal to, we are solving the capacitance now of this capacitor connected in series now. C1 is what? We are going to do 1 over C1 plus 1 over C2 plus 1 over C3. Then we substitute. We are going to see, let's substitute first of all. 1 over, what is our C1? 1 plus 1 over, what's our C2? 2 plus 1 over, what's our C2? 3. What do we do here? Because we have 3, I don't like doing LCM style. I will pick 2, solve 2, then what I get for the 2, I will use it to solve for the third one, and so on and so forth. But if we have 4 here, 4 now, for example, just do the 2 first. You do another 2, then you use the 2 answers you get to do for the final one to get your answers. So this one will do 2. Just times the 2 denominator to get numerator, and plus the 2 denominator to get a denominator. All right. So 1 times 2 over 1 plus 2. All right. 1 times 2 is what? Is 2. Right? Equal to 2 over 3. All right. So we will now use the answer, what we get here, to do for this one. All right. We are not going to have, we are not going to be left with equal to 3. No, we are not going to do it like this. This one will give us 0 points, equal to 0 point, is it not 0.1 or so? I'll be 0.2. Then we are now going to have, this one is going to give us 1 over 0.1. That's how we are going to put it. They will now use it to solve with this final one, this third one, plus 1 over 3. We will now do it again. 0.1 times 3 over 0.1 plus 3. This one will now give us our final answer. This will give us like 0 point something. That's already 0. This will give us 3. Okay. So what is the answer? The answer is undefined. In mathematics, undefined. But here, we just pick 3 as the answer. So 3 farad. Let's now observe energy stored in a capacitor. Energy stored in a capacitor is the total energy that the capacitor holds. All right. So it's giving us E, which is energy, is equal to 1 over 2. That's half CV squared. It has about 3 formulas. Okay. It can also be given as energy equal to Q over, okay, half Q, 1 over 2Q, 1 over 2Q over C, which is what? The capacitance. Okay. So it all depends on what you were given as your parameter when you are solving. If you were given capacitance and volt, EMF, you use this one. This one is going to be better. If you were given This one, charge, which is in coulomb, and capacitance, this one is going to be better. So you have to make your discernment and pick the best that is okay for you to solve. What are the factors affecting capacitance of a capacitor? Capital letter C. Capacitance of a capacitor increases with what? Permittivity area. When the permittivity area increases, capacitance increases. Okay, so increase permittivity area equal to increase capacitance. Okay, or area. Okay, increase area or permittivity area. Anyone you want to put area or permittivity area. All right. Then another thing that can affect it again is dielectric. What is a dielectric? A dielectric is a substance that allows the transmission of charge without the transmission of substances. All right. So if you put the substance now between here, you have positive charge and you have liquid here. Okay, liquid. And here we have, let's say we have another liquid again, a different liquid, but here we have negative charge. You know what dielectric does? It allows charge to be transmitted. Charge can move from here to here, but the liquid is not going to miss. That's what dielectric does. Okay. So capacitance decreases with distance. Okay, so increases with area, decreases with distance, and is affected by dielectric. So that's that for that. Ensure to answer the sweet and beautiful questions you have under capacitance. All right. Ensure to answer those beautiful questions. I think we'll go into electricity, and after electricity or electric circuit, we draw the curtain. We draw the curtain for today. We are going to have one final class. Electricity, is there anything we need to look at for here? Okay, let's just look at the electricity cells. Cells are batteries. Okay, in physics, in chemistry, cells are batteries. In biology, cell is what? The basic unit of life. But here, cells are batteries. All right. Battery usually converts what? Or cells. Battery or cells usually convert chemical energy to electrical energy. Okay, cells slash battery. Convert what? Chemical energy to what? Electrical energy. That's what cells does. All right. We have majorly two types of cells. We have primary and secondary cell. Or you can call it simple and complex cell. Cells. Simple, complex. Complex. Or you can call it primary, secondary. This can be called voltaic cell. Voltaic. So the simple voltaic cell, we have various cells like the zinc copper cell. We have zinc copper cell. Okay, zinc copper cell, whereby we have zinc as electrode in copper 2 tetraosulfate 6. Okay. What are the defects of this cell? The defects include polarization. Defects include polarization. Polarization. What is polarization? Formation of hydrogen bubbles in the cell. Okay, and this leads to destruction of the cell component. All right, gas buildups in the cell, and what do polarization cause? In turn, reduces what? EMF. Electromotive force is reduced. Another one is local action. Local action. And what is local action? When zinc dissolve in acid, okay, the electrode start dissolving in acid. Electrode dissolve in acid. In acid. That's why. And in this case, what is the electrode used? Zinc is the electrode used. Okay, zinc is the electrode used. Zinc is the electrode used. So how do we correct these defects? Use depolarizers now. You use substances called depolarizers. Correction. Use depolarizers. Depolarizers such as manganese 4 oxide. Also amalgam. Amalgamated zinc. Okay. Prevents depolarization. Polarization. Okay. Polarization of cells. What are solar cells or photovoltaic cells? They are also called photovoltaic cells. Photovoltaic cells. Okay. They are cells that convert light energy or ultraviolet energy to electrical energy. For example, solar panel. All right. So now let's look at other cells or other batteries. We look at other batteries and their components. All right. Let's clean up this place. We just look at the most basic voltaic cell. That's what we just looked at. Okay. And it's this voltaic cell that usually gets those defects like polarization. Okay. The voltaic cell. Then let's look at some simple cells. Okay. Or primary cell. We have Daniel cell. And in Daniel cell, we have zinc tetrasulfide 6 and copper in copper 2 tetrasulfide 6. Okay. So we have zinc. This one is one of the electrode in zinc tetrasulfide 6. Then we have copper in copper 2 tetrasulfide 6. Okay. So this zinc is usually placed in a porous pot. All right. It's placed in a what? Porous pot. We have another cell called Leclanche cell. All right. Leclanche cell contains the electrolyte. This is the electrolyte, okay, of the cell. This one, zinc and copper 2 tetrasulfide 6. So we have the anode of this cell is usually made up of zinc. Anode is positive. Anode is negative, right? The anode is usually made up of zinc. Okay. In this, cathode is usually made up of this. This one, anode negative, cathode positive. Okay. All right. So we have the Leclanche cell, and there are two types: wet Leclanche cell, where you have liquid electrolyte in it. Then you have dry Leclanche cell, where you have paste, electrolyte paste in it. And what's the electrolyte paste? Ammonium chloride. All right. That's the one you have in dry Leclanche cell. This paste. So, what is the meaning of EMF? EMF is the force that drives current. Is the force that drives current throughout the cell. Okay, or the work done of driving current throughout the cell is measured in volts. All right, EMF. The efficiency of a cell is equal to, the efficiency is represented with this, is equal to EMF over terminal voltage. EMF over terminal voltage, that's the voltage that it ends in terminal. Terminal voltage times 100%. All right. Now let's look at secondary cell. Under the secondary cell, we have two cells there. We have nickel ion and lead acid accumulator. All this one, lead accumulator cell, you can recharge them. Most of these cells, like Daniel cell, Leclanche cell, they are not rechargeable. Simple cells are not rechargeable, but complex cells, secondary cells, primary cells are not rechargeable, but complex cells or secondary cells are usually rechargeable. Okay, so you have lead acid cell. Usually they can still call it lead accumulator. Contains what? Lead. All right, lead tetrasulfide 6 usually provides high current. So simple cell usually provides low current, okay, for a short period of time. But this one can give you high current. Complex cell can give you high current for a longer period of time. Okay, simple cell can be stored for long without it discharging. Okay, it's not going to discharge. You can store it for 1 year, 2 years. But complex cell or secondary cells, you can't store it for long. That's why when you keep your phone before 3 days, 4 days, 5 days, 1 week, it runs down even after you've charged it 100%. All right, but you can keep all those small Tiger battery. You keep it for years and it still retains its charge. Anytime you put it inside the remote, all those remote battery, it functions properly. Okay, you still have charge in it. All right, I think we are close to the end of this class. We have less than 10 minutes to go. Then the second one is, this one is commonly used in car batteries. All right, remember they are rechargeable. Okay, the second one is NECO ion battery. Nickel ion battery. That's the second one. This one is more durable than lead acid battery. More durable. But the disadvantage is that it is what? Expensive and has a lower efficiency. All right. Terminal voltage. Is terminal voltage not potential difference? So also remember that terminal voltage is potential difference. Where we talked about that formula, that efficiency is equal to EMF over terminal voltage. You can also write that terminal voltage as PD, potential difference. That's 100%. All right. So that's that for that. Electric current. What do we have to know about electric current? Current electricity is the study of electric current in a circuit. Okay. The EMF is known as the voltage of the cell. The force that drives what? Current around the cell. But potential difference is across load. The volt across load. EMF, voltage of cell. PD, potential difference, volt across load. Okay. Ohm's law states that the amount of current passing through a metallic conductor is directly proportional to the resistance, provided that the temperature remains constant. All right. It states that V is equal to IR. That's Ohm's law. Where V is equal to voltage, or let's say volt, I equal to current, R equal to resistance. Okay, so it says the amount of current passing through a metallic conductor is directly proportional to its what? Its resistance, provided that the temperature remains constant. So not just the temperature. Ohm's law tells us that the amount of current passing through a metallic conductor is proportional to the product of the current of the product of the volts and the resistance. All right, provided that the temperature and all other physical, all other physical determinants remain constant. All right, so we are left with this V equal to IR. If we are looking for V, if we want to do subject of formula, we can then say I is equal to V over R. We can also say R is equal to V over I. All right. So this is Ohm's law for you. Remember, resistivity is directly proportional, is equal to resistance. So when the resistance of a wire increase resistance equals what? Increased resistivity. All right. So resistivity is usually written like P, like this. Okay, resistivity P. All right. So increased resistance equals increased resistivity. Increased resistance 2 equals what? Decreased current. All right. Okay. Increase when the resistance is high, the current flow decreases. All right. Let's get to EMF. Here is our EMF. EMF is measured with an instrument called potentiometer. Potentiometer is a type of galvanometer used to measure EMF. Okay, it's the most suitable to measure EMF. All right. Calculating resistance in series and resistors in parallel. All right, it's the same thing. All I've been explaining here. Now the same is the same method. Calculating it is the same method. No difference there. Okay, it's only capacitance. When you want to calculate capacitor, in capacitance and capacitor, that's when you do the opposite. Apart from capacitance, every other thing that is connected in series or parallel, you either use when it's connected in series. That's series means in resistance, series connection means that it is connected straight. Okay, maybe this one is resistance 1, this one is resistance 2. No branch, is connected straight. Okay, the formula is usually given as this: resistance is equal to R1 plus R2 plus R3. But if it's in capacitance, if it's connected in series, we will now do that 1 over plus 1 over. You see, it's solely in capacitance that is opposite. Then in parallel resistance in parallel. How do you do that? How do we know that the resistance is in parallel? When you start having branches, that's resistance in parallel. For example, you have R1 here. It goes like this. You have another one here again. Can you see branch? R2. It goes like this again. You have another one here again. Okay, R3. It goes like this. You have another one again here, R4. It goes like this. You have another one here again, R5. You see? So this one is resistance in parallel. There is branching. Okay, so we can easily say when we have something like this, this one is one resistance, this one is another one, this one is another one. Okay, this one is another one. All right, so this one is connected in parallel, is branch. But here we can still have resistance in series too and resistance in parallel in the same circuit. Okay, so here is another one now. This one is resistance. Here again, this one is another resistance. So this one is connected in series. This one series because it's straight, no branching. This 4 is connected in parallel. So we are going to name this resistance 1, resistance 2, resistance 3, resistance 4, resistance 5, and resistance 6. So if you want to solve this now, they say calculate the total internal resistance. You are going to do for the parallel separately. How many parallel do we have here? 1, 2, 3, 4. You do the parallel separately, you get your answer. Let's say after doing the parallel, you got 4 as your answer. Then you do the series separately, following the series style, and you get your answer. Maybe you get 2. What you have to do to get the total internal resistance, you plus it, plus your 2 for series, you get your 6 as total internal resistance. Okay. But if you are told to look for the resistance in series, you solve only the resistance in series, the 2, add 2 of them, you get your answer. You come out there. If you are told to look for only the resistance in parallel, you add 2 of them and you get your answer. Okay. As simple as ABCD. So there's something we have to note here. Something very, okay, so what's the formula of this one in parallel? 1 over R is equal to 1 over R1 plus 1 over R2 and so on and so forth. All right. There's something we have to do here. One sweet formula. After solving your total internal resistance, they can ask you to look for the current, or ask you to look for the resistance, or ask you to look for whatever. Okay. You can simply apply the electric formulas. Okay. You have electricity formula like I square ROT. Okay. You have another one, I VT. Okay. You also have another one again, I square VT. Okay. These are electricity formulas. Okay. Then you also have another one, the one that relates current, resistance, and volt. Okay. That one is I is equal to, that's Ohm's law. You will now apply Ohm's law here, V over R. V over R. Okay. So you now use Ohm's law to finish it up. Okay. Maybe you are giving volts somewhere in the circuit, maybe 2 volts. For you to now get the current, you will now use the volts and plus your total internal resistance. Maybe your total internal resistance that you got after solving is 4. You will now say I is equal to V over R, which is 2 over 4 to get your what? 0.2, right? So this will be your current, 0.2 as your current, ampere. Okay, as your current. So if you are asked to, if you can still use this Ohm's law to find resistance, you can still use this Ohm's law to find volts. Okay, maybe you have current and resistance. You can use it to find volts. All you have to do, V is equal to IR, I times R. Okay, that's that for that. I think that will be all for this class. In our next class, we are going to do energy and power, and that next class is going to be the final class.